Okay, let's backtrack just a hair so we can sort of fit things together. We left off last time talking about Dalton's Law of partial pressures. And all it says is that when you measure the total pressure of a gas, and it's a mixture of two or more gases, and that total pressure is actually the combination of pressures that are due to one gas and plus the pressures due to the other gas. And we use that to solve this problem where you have a gas in this vessel with that volume, and we open this valve so that it'll mix with that gas. And how do you solve the problem? Well, you need to use two laws. You need to use Boyle's law that we're going to investigate today in the lab, and you need to use Dalton's law of partial pressures, because there's no one way. You can't just look at the problem and zen out and get the answer. Right? You got to treat it as if it's two separate problems. This one is being sucked into a vacuum on one side, and then this one you treat it as being sucked into a vacuum. And you calculate the pressure that's due to this one, and then calculate the pressures due to that one, then you add together. And that's how we solve that problem. And that's what all these calculations are for. Okay. Now we're ready to go talk about changes of state. We've already talked about the different states of interest for this class, that solids, liquids, and gases. There are a couple others, but they're very exotic and we don't want to deal with them. So we only have to consider those three. So when something changes from one state to another, its identity remains the same. It's like melting ice. Water, you still got water, only it's liquid now instead of solid. So it didn't change its chemical identity. That's a physical process. And more often than not, it's accomplished by adding or extracting heat from the substance. That's not the only way, but it's the most common way. And sometimes when you use other ways to change states, you're actually combining two or more different processes, like changing pressure, like changing air pressure. We used to do that with our freeze dryers. We collect plant samples from the field, put them on dry ice in the field because it couldn't carry enough liquid nitrogen, but it would get them cold enough when it stopped the biochemical processes before we got back to the lab. Then when we got to the lab, we'd dunk them in liquid nitrogen, and that would complete the process. Then we'd stick them in a freezer until we got a chance to put them in the freeze dryer. Well, the freeze dryer does two things. It decreases the air pressure inside the chamber, and it adds a little bit of heat. And what that causes ice to do is to sublimate. We haven't defined that yet, have we? It changes directly from a solid to a gas. So that's what freeze drying does. The first commercial application of freeze drying, I think, was Sanka coffee. They had those little chunky crystals. I don't know if you've ever, any coffee drinkers in here, if you ever tried that. But supposedly the freeze drying retained all the flavor components of the brewed coffee. So when they freeze dry it, grind it up, sell it, all you have to do is just dump a couple of spoonfuls in your cup with water and tastes just like you brewed it fresh. Anyway, these are physical changes that take place. These are different types of processes that change state. And I find it instructive to use a triangle. So if you've got the state of gas here, and then you've got liquid over here. Hope I'm giving myself enough room. And you've got solid over here. Right? Then you can go from liquid to gas. And that process is evaporation. Okay. Go back the other direction. We call that condensation. Okay. If you go from liquid to solid, we call that freezing. If you go from solid to liquid, we call that melting. Now, if you go from solid to gas, I mentioned that one earlier, that's sublimation. Okay, go the other direction from gas to solid, that's deposition. So those are the 6 physical changes that occur in phase change in a nice little diagram. Okay. Oh, there it is. That's even a prettier picture than I drew. Get that out of the way. And in these processes, actually this slide is a little better because it describes what's happening to the heat in the process. In other words, to go from solid to gas, you have to absorb heat. And just what that means is that the molecules of the solid have to speed up. They need energy. So they absorb energy. So heat has to be absorbed in order to go from solid to gas. Or from a liquid to a gas, same thing, you have to absorb heat. Or you go from a solid to a liquid, you have to absorb heat. Go the other direction, the heat is released. Okay. Oh, sublimation, perfect example. Dry ice, solid carbon dioxide. Have you ever played with that?
Yes.
It's fun.
It's hot. It burns you. Not hot, but it burns you.
Yes, it'll freeze or burn you if you hold it too long. You throw it on the ground and you just watch it steam.
We put it, because that's where our blood comes in the lab.
Mm-hmm.
Sometimes it dries. And we'll throw it in that sink and it's big old steam
Mm-hmm.
coming up.
But that's sublimation. Okay. So when we describe the movement of heat, there are other terms for that. And it's also good to look at the movement of heat in terms of the system. You can define what the system is, then it's easier to relate the terms that are applied to heat movements. Okay, so, and we use a Q for heat, just a small q. Okay, so the amount of heat that, and it's all relative to the system. There's a system and then everything else is surroundings. Although you can limit these surroundings, they don't have to be the entire universe. You know, you could block it off. So you have system here, and this much is surroundings. Then if heat moves, let's use this term. If heat moves into the system, right, it's given a positive sign, and heat moving into the system is endothermic. So you have to define your system. What is your system? Well, sometimes it's easy and sometimes it's not. If you have an ice cube, that's easy. The ice cube is your system. So it absorbs heat and turns to liquid water. Melting, that's a good example. If this is a solid, it goes to a gas, it still has to absorb heat to change phase into a gas. It goes from liquid, solid to a gas. Okay, or evaporation, if it goes from a liquid to a gas. And you always have to add heat. And it's a positive value. If you put a number on it, and we can do that, we can say how much energy is absorbed for so many moles of compound. then the sign will always be positive because everything is relative to the system. It's being added to the system. If it goes the other direction, then the sign will be negative. And I think that's probably the next slide. Okay, so exothermic process would be heat would move out of the system, and then the sign would be negative. Everything's relative to the system. Loses heat, it's a negative operator. Freezing, if you go from liquid, to solid, you have to release heat. If you go from gas to solid, no, excuse me, yeah, deposition would be gas to solid. Condensation would be liquid to gas to liquid. Any of these processes require that heat be released. So what's happening inside the substance is the molecules are slowing down. They're giving up energy. In other words, if they give up energy, then they are losing kinetic energy. Okay, they're not moving as fast. And that allows any intermolecular forces that operating between the molecules to start taking effect. And if you move enough energy, then there's enough to change the phase. Like you can go from liquid to a solid, move enough energy, they slow down, slow down, start sticking together. So it's a balance of energy. Okay. That's just to check. What's the difference between endothermic and exothermic? Well, endo means into and exo means out of. So there you go. And thermic is heat. So heat goes in, heat comes out. That's what those terms mean. Okay. Let's see. So if you're going to evaporate a liquid and make a gas out of it, that doesn't mean you have to flash the whole amount of liquid into a gas instantly. The conversion from the liquid to the gas occurs at its surface, right? So remember, liquids, they have to be in a container of some kind. They can't hold their own shape. So there's always a surface of the liquid. And it's, depending on the liquid and the temperature, it's changing from liquid to gas at the surface and absorbing energy to do that. And it has to have enough energy to overcome any attractive forces that are holding the liquid together. So it needs energy. That's why when, especially in the summer, when your temperature is elevated, if you sprinkle water on your hand, it feels cool because the water is evaporating. And in order to do that, it needs energy. Where does it get that energy? It's coming from your hand. So your hand would be the surroundings, and the water on your skin would be the system. And if your hand is pumping energy into that water to make it evaporate. Okay. We can measure the rate of change. Okay. How fast does the liquid evaporate? Well, qualitatively speaking, you speed it up when you increase the temperature. You're adding more energy. That means more molecules now have enough energy to escape at the surface of the liquid. So you're increasing the rate of evaporation. And I just described this one, the cooling effect of a liquid when it evaporates. We use that in our air conditioning systems too in the summer. You have Freon, some kind of Freon in the system, and it goes through a compressor, and the compressor squeezes it down. It gets hot, and then it runs through a set of coils that expel that heat to the air. So that's why if you hold your hand over your air conditioning unit outside, it feels hot in the summer. It's hotter than the surrounding air. It's getting rid of that energy so that you can condense the freon from a gas to a liquid. Okay. Then you send the liquid into your house, and it goes through another valve and a set of coils, and it's allowed to expand from a gas and phase change from a gas, from a liquid into a gas. When it does that, it needs energy to do that. And it sucks that energy out of the air that's blown over it. Okay, cools down the air, then that air is blown into the house, and there it is. So what's a vapor? A vapor is a gas. It's just another word for a gas. And it's associated with what would normally be at those temperatures, pressures, you would normally see as a solid or a liquid. So for our dry ice, when you throw it in your sink, you see a gas coming off of it. You actually don't see the gas. The carbon dioxide that comes off of that dry ice is so cold, it condenses the moisture in the air and makes a fog. So you're actually seeing the fog of water vapor that's condensing into a cloud, but it's caused by this vapor coming off of your solid carbon dioxide, your dry ice. So, and you'll see this term used often when we're, say we confine a liquid in a flask. So the liquid is here, and it's losing molecules to this space up here. Right? It'll just continue to do that until the liquid's all gone. But if we plug it, put a stopper in that, then the molecules will continue to fill this space until they reach a point where they start to return. So you get both processes going on at the same time, evaporation and condensation. And at some point, you get the same rate of condensation as you do evaporation. And now you're at equilibrium. And you can measure the pressure inside this headspace. That's the vapor pressure of this liquid at a given temperature. Okay, so that's another way of using this word vapor to describe the pressure that's inside a closed vessel. Okay, let's identify whether heat is absorbed or released during the evaporation of the liquid. Okay, so let's think. What's the phase change? If the liquid evaporates, it's going from low to high or high to low energy. It's going from low energy to high energy. Because the molecules, once they get into the gas phase, they're a lot further apart and they're moving faster. So we have to add energy to it. That means heat is absorbed. Not released, it's absorbed. And that's kind of stupid, actually. You can't have it both ways. You can describe heat is absorbed by the liquid and released by the gas if it returns to the liquid. But that's not what this says. Okay. Heat's neither released nor absorbed because all molecules in the liquid possess the same kinetic energy. That's a confusing statement, typical of multiple choices. Multiple choice questions are designed, and word problems, as a matter of fact, are designed to confuse. If they don't confuse, that means you know the material. That's how we get around having to grade essay questions, or short answers for that matter. Okay, so heat is absorbed. That's it. That's the simplest answer. That's the answer. Okay, this was, If I'd have known this slide was coming, I wouldn't have wasted your time with my description. So here's our liquid, and some of it, initially, there are no molecules in this liquid in that space. They start to occupy that space. I hope you're wondering if this liquid if everything in there is at the same temperature, then that implies that all the molecules in there have the same kinetic energy, because temperature is a measure of the average kinetic energy of the substance. So if they all have the same temperature and they're all moving at the same speed, why do you get liquid becoming gas? Well, the reason is that the kinetic energy of the molecules is not uniform. Notice I said temperature is a measure of the average kinetic energy. Right? You have a spread. Have you ever heard of the bell curve? Some instructors use it in grading. I don't. But it's typical of most natural populations. You'll have so many with this much kinetic energy. Then you'll have some with this much, and you have some with this much. And if you add them all together, then you find that actually should be down here. And this is numbers of molecules. Okay, so very low kinetic energy, they're not many. Most of them are in this range. Most of them, 90% will be in that range. With this much kinetic energy, you'll have that many. But you'll have a few that are out here with at the high end of the kinetic energy. They've got enough to escape from the surface. So those are the ones that move into the vapor phase. And then you reach a point where they're constantly going back and forth. And then these molecules here, they will also have a spread of kinetic energy. And some of those will have low amounts of kinetic energy, so low that they'll return to the liquid. Okay, so you get that exchange. Eventually you reach an exchange where the condensation rate is equal to the evaporation rate. And that's an equilibrium state. Okay. That's probably more information that you wanted, but I thought it might be useful. That's known as a physical equilibrium. We can describe chemical equilibrium also. We've written balanced equations, right? Okay. We started off writing balanced equations with a single arrow from left to right. Reactants make products. When in fact, all reactions go both directions. They make products, and then the products can return to reactants. And depending on the reaction, it could be weighted heavily toward products. So for all intents and purposes, it makes nothing but products until all the reactants are gone. But some reactions go backwards and forwards fairly freely. So you have lots of reactant and lots of product. And there's a way to express that. But right now we're talking about physical equilibrium. So equilibrium can occur in both scenarios, either physical or chemical. So the general definition is two opposite processes occur at the same rate. That's the simplest definition of equilibrium. And in the physical equilibrium, that would be a change of state from one to the other. And when that happens, the interesting thing is when that happens, you don't see a change, right? If we cap that flask off and let it sit there for several hours or maybe days, then if you make a mark on the flask you'll see the level of the liquid drop. But eventually, it'll drop and stop moving. So that's what we observe, the macroscopic. We see that it's not moving anymore. So at that point, we have an equilibrium. On the microscopic scale, activity is furious, backwards and forwards from liquid to gas. But on the macroscopic scale, it's like nothing's happening. Okay, so I mentioned that you can measure a pressure in that headspace. If you cap it off, then at a given temperature, it will produce a characteristic pressure. Some liquids produce high vapor pressure, some produce low. So water will produce a low vapor pressure at the same temperature. All right, we've got a constant temperature for these liquids. So liquid water has a low vapor pressure, whereas ether, well, let's be specific. Diethyl ether, which they used to use as an anesthetic in the operating room, which is sleep, that and chloroform, believe it or not, will produce a much higher vapor pressure. Simply because of the way of the structure of the molecule and the type of forces that hold them together. Water has, let's see, we talked about polar versus non-polar. We did that, okay. Water is a polar molecule. So it has a strong intermolecular interaction between the positive and the negative, slight positive and slight negative sides of the molecule. So there's a strong force there holding it in that liquid phase. It takes more energy to make a vapor out of it. Whereas diethyl ether is a nonpolar molecule. It has an oxygen in the middle, and then it has two ethyl groups. On either end. So it's balanced, it's linear and balanced. So it has no poles. There's no interaction among the molecules. So it, at the same temperature, it leaves the surface of a liquid much, much easier. Okay, so it produces a higher vapor pressure. More gas in the same space makes more pressure. And we described, yeah, I know we did, Boyle's Law last week. Okay, so that's simply a response to Boyle's Law. If you've got the same or roughly the same volume in that headspace, but you cram more molecules into it, actually that's not Boyle's Law. That's actually it's nobody's law. It's the combined gas law. All right, so this is initial. This is final. So if you hold the temperature constant, right, we can remove those factors. The volume is constant, right? Volume is constant, so we can remove that factor. So now we have a pressure moles response. If you fill that same headspace with more moles, you get higher pressure. So that's where the added vapor pressure comes from a more volatile liquid. The EPA and OSHA have standards for the amount of volatile organic compounds, VOCs. They have standards for things like solvents and paint, right? You can't exceed a certain amount. And they measure that by the vapor pressure that it produces. They just stick some paint in the vessel and wait for it to equilibrate and measure the pressure. If it exceeds a certain amount, and they send the company a nasty letter and say, you got to fix it. Okay, so let's see, where am I? Right, the magnitude of the pressure depends on the nature of the compound or the element, as the case may be, and the temperature of the liquid. So a higher temperature will produce a higher vapor pressure. Water we used as an example of producing a low vapor pressure. And I used diethyl ether, but helium would do the same thing. Very weak attractive forces with helium. So if you have liquid helium, it's going to be extremely cold. So at those temperatures, if you compare the same temperature for water and helium, water vapor pressure at those temperatures, at those low temperatures, it's going to be immeasurable. Liquid helium is very close to the coldest liquid you can get, the coldest substance. It's like about 4K, just above absolute zero. Okay, well, there's an ether. There you go. That's dimethyl ether. This is the methyl group, and the one I showed you earlier was the ethyl group, CH2, but the argument's the same. It's a nonpolar molecule. So the attraction between molecules is very, very low. These are volatile substances. And they tend to evaporate at room temperature. In fact, there are some things that evaporate so quickly that as soon as you open the vessel, somebody at the other side of the room can smell it. There are some compounds that are like that. There's one sulfur-containing compound, and that's why you can smell it over there, because it's got sulfur in it. It would be difficult to smell this one right away. Some perfumes are very volatile. Well, they actually have a mix of compounds in there that have high vapor pressure. So you keep them in your sealed bottle. If you leave the bottle open, the room will smell nice for a while, but it won't be long before all your perfume's gone. It evaporates really fast. Okay, let's say a liquid in a closed container evaporates for a short time and then condenses as the number of vapor molecules increase. So the key here is there's a liquid and the container is closed. So it's going to start developing that vapor pressure. The process is known as what? Well, if it evaporates for a while and then it starts condensing, then the process would be physical equilibrium. It reaches a point where those rates are equal. All right, let me see, how far am I going? 13. That's the end of the chapter. Boiling. So what process is boiling? Well, boiling does change a liquid into a gas, and it happens at a certain temperature and a certain pressure. So if you want to cook something, or you want a can in your pressure cooker, those operate at various pressures. I think they have a range that you can do 5, 10, 15 PSI, depending on how much of that top thing you sit on there. And then when it starts spitting, it's reached its pressure. It's reached that pressure inside. You know it's at 15 PSI above atmospheric. And why do we do that? Right? What's the advantage of increasing the pressure on that liquid? It takes a higher temperature to make it boil when you increase the pressure. So you can cook food faster, or you can guarantee that your canned food is safe, because under those conditions, 15 PSI for how long? 20 minutes, I think, is sterilization time. Then all microbes in your inside your containers are dead. And we do it because the boiling point increases with pressure. Okay, let's see. So this boiling occurs when the vapor pressure of the liquid is equal to the external pressure. So inside your pressure cooker, the boiling won't start until you reach a higher temperature. But if you go to base camp on the slopes of the Mount Everest and try to cook your lentils, it's going to take a while because your water boils at a much lower temperature. Instead of 100 degrees, it'll boil at 85 degrees Celsius, which means that there's not enough heat going into your food. It takes a long time to cook it. So it's a commercial operation now, climbing Mount Everest. So they probably have, the Sherpas have probably gotten savvy, and they probably rent or will sell you a pressure cooker, a small pressure cooker that you can operate at those heights. Either that, or you just take MREs with you, meals ready to eat, and you just add water to them, mix them up. I guess if you're going to rough it in the wild just to go up the side of a mountain, then that's not too much to ask. Okay, so when boiling starts, the formation of the gas, the evaporation, occurs inside the liquid. Now you've got enough energy input to overcome the external pressure. Think of it as pressure's bearing down on the surface of the liquid, and it's keeping those molecules in the liquid phase, except for a few of them. So if you add more heat and they're moving faster, now they can kick butt, move out. So where do these gas pockets form? They form near the heat source, right? Down here at the hot plate. So they're going to boil down here. And, well, I don't want to digress. Let's just move on. So that's known as the boiling point. Now, the most efficient way to measure the boiling point is with a small volume. And actually, boiling point measurements, and melting point measurements for that matter, are conducted in special instruments, where you have even a little capillary with your liquid in it. And you put it in your device, and you've got a microscope that you can watch it with. And you see at what temperature. Temperature is ramped up slowly. And then you can see when it starts, and you can note the temperature. That way, you don't have the influence of all this extra pressure that the liquid is bearing down on this right here. Okay, but when it reaches that point, the temperature of the liquid no longer increases. So if we look at it in terms of this is a type of phase diagram. So as your temperature increases, and this is, say, just progress. So you can increase the temperature of your solid like that, and then when it starts to melt, temperature stops changing. Here, the temperature of the energy that you're adding is used to make the particles move faster. When you get to this point, where you're going from solid to liquid, now all the energy is being shunted into phase change. And it'll stay at that temperature until all the solid's gone and you have nothing but liquid. Then you start heat. The heat you're adding will make the temperature increase again. So this is nothing but liquid, okay? Until you get to the boiling point. When you get to the boiling point, it stops going again, stops increasing again. And now your phase change is going to gas. Okay, when all the liquid's gone and nothing but gas is left, then you can continue to heat it like that. So that's why if you want a constant temperature, say in the laboratory, a good way to do it is to have ice and water together in the same container. As long as you've got both of them there, you haven't melted all your ice, you've got ice and water together, the temperature is stable. Okay. No matter how much energy it absorbs from the room, As long as you've got ice and water together, liquid water, then the temperature will be stable. Okay. All right. So that's the boiling point. Now, what do we mean by normal boiling point? Normal boiling point, let's see, that would be here, this temperature. Right here. The normal boiling point is the temperature at which the liquid boils under 1 atmosphere pressure. Okay. 760 millimeters of mercury is 1 atmosphere. See, why do I have that blue box down there? Oh, explanations. Yeah, I already described that, going up to Mount Everest. So even in Denver, if you live in Denver, it takes longer for you to boil an egg there than it does here or on the coast, because you can't get your water hot enough, right? If it's boiling, you're stuck at that temperature. And if the temperature is the boiling point is dependent upon air pressure, external pressure, then the only thing you can do about it is stick your egg in a pressure cooker and get the temperature back up. Okay. Oh, here we go. The top of Mount Everest, boiling point of water is 70 degrees. So maybe on the side of Everest, it'd be closer to 80 degrees. You're not on the top yet. Nobody's going to climb Mount Everest and sit on the top and cook their meals. While they're doing it, they'll run out of oxygen because you can't stay up there very long without assistance. Anyway, let's see. If you go down below sea level, right, you'll start to increase the boiling point of water above 100 degrees. Death Valley, I think the Dead Sea is even lower than that. Okay, so there's the definition of a boiling point. And then we expand that definition to, well, restrict that definition to normal boiling point would be at 1 atmosphere pressure. Okay, what's the vapor pressure of water at 100 degrees C if it's boiling? This is what we've discussed so far in reverse. If your water is boiling at exactly 100 degrees and it's pure water, doesn't have anything else in it but water, that's important also, for different reasons. If it's boiling at 100 degrees Celsius, then you know that the vapor pressure is 1 atmosphere, because the vapor pressure equals the external pressure at the boiling point. Okay. All right, let's see. Oh, did I go too fast? I don't see anybody writing. I'm going to go to the next slide. So I mentioned these before, intermolecular forces, or intra versus inter. Intramolecular forces are those that hold molecules together, like the bonds that hold oxygen to hydrogen in the water molecule. Right. These bonds are intramolecular forces. And you have a couple of types. You have the ionic bond and you have the covalent bond. We've talked about that before, I think. Those are within the molecules. And they have to be very strong in order to hold this molecule together. Because if it's going to undergo physical changes, then we can't put so much energy into it that we break those bonds. Because then you have a chemical change. And we can't do that if we want physical phase changes only. So the intermolecular forces are those that occur between molecules. So for water, we know that it has polar bonds this way, that way, and then overall is polar that way. So this is the slight negative end and this is the slight positive end. And when they interact, Those are the intermolecular forces, those that are between molecules. Yeah, the between molecule forces. So you get the positive end lining up with the negative end, and you get those electrostatic attractions. Okay. Now, how do they compare with strength? Well, the intermolecular forces are much weaker than the intramolecular. The bonding forces have to be stronger than the intermolecular forces that hold the molecules together. Think about it. If it wasn't the case, if the intermolecular forces ever became stronger than the intramolecular forces, they would rip that molecule apart. So the intermolecular forces have to be weaker as a practical matter. And like I said before, nature just does what it does. And we have to invent this stuff to try to explain it. Okay. There are different types of intermolecular forces. One that we've alluded to before is where the one dipole interacts with another dipole. So if you have another water molecule here, this is the negative end, this is the positive end, you're going to form an intermolecular bond here. And actually, this is a special kind of bond where you have an electronegative, did I describe that yet? Electronegative atom, one that likes electrons, that pulls electrons to itself. And those are characteristic on this right-hand side over here. Non-metals. They like to attract electrons. So even in the bonding situation, they'll try to pull electrons away from the other atom if they've got a stronger pull. So that's why you get that uneven distribution of electron density. So we get the slight negatives on this side, the slight positive on this side, and then the hydrogen bond is a special kind of dipole where you have to have hydrogen bonded to some other atom that is very electronegative. So oxygen is a good example. Fluorine will do that also. And then, let's see. I think nitrogen is given credit also. That bond will produce enough strength to develop this hydrogen bond. And the hydrogen bond is at the high end, the strong end of the dipole-dipole interactions. And wherever you see the accumulation of these types of bonds on a molecule, you're open to hydrogen bonding. So when you see even bigger molecules like ethanol, the drinking kind, like that. That's ethyl alcohol. This is available for hydrogen bonding. Right? So this is going to be slightly negative, and this will be slightly positive, and it can form hydrogen bonds with its neighbors. Let's see, what's the formula here? Two carbons, right? Two carbons. 2, 5, 6 hydrogens, and 1 oxygen, right? That would be the molecular formula. Okay. What if we change the structure? Instead, we put the oxygen in the middle. And then we take 1 carbon over here and 1 carbon over there. And then we got 6 hydrogens, right? We've used up the carbons, used up the hydrogen, used up the oxygen. Now we got hydrogens, 6 hydrogens. So this molecule has the same formula as that molecule. But where's the hydrogen bonding? Doesn't have it, because that oxygen is not attached to a hydrogen. So it doesn't have that ability to form the hydrogen bond. This is that dimethyl ether that we looked at before. And that's why this one has a lower vapor pressure than this one, because this one has stronger intermolecular forces holding it in the liquid phase. Whereas this one, dimethyl ether, I mean, you open the bottle and within minutes, it's empty. Stuff comes out of there and you can smell it across the room. Okay. So if you have a molecule that doesn't have access to these stronger intermolecular forces, like the dipole interactions. In fact, you can get a dipole ion interaction. Oh, here it is. Yeah, dipole ion interactions, and they're electrostatic, right? If you've got a dipole here, and then it comes in, you add some ionic compound to it, like sodium chloride, you will get a bond between that positive and this negative. So you can get those types of interactions also. And you can get ion-ion interactions. In solution, you've got water, say, and you've got sodium, and then you've got chloride ions. You can still get interactions between the sodium and the chloride ions. But if you don't have these stronger interactions, right, where we can identify a slight positive and slight negative, where they can interact with one another electrostatically, but we still have the physical evidence for intermolecular forces that are much, much weaker than this. And those are the London dispersion forces. That's not London, England. That's London person, named after a person. So, what do we mean by London dispersion? Well, dispersion refers to the electrons, the electron density. So if you have a molecule that you know is nonpolar, like this dimethyl ether, well, that's not a good example, because this bond is polar, but they're both polar in opposite directions, so they cancel one another out. But what if you have a molecule that's nonpolar, and the bonds are nonpolar too, like nitrogen gas? Given out on me. Nitrogen gas is like that. Right? You got two, the same nitrogen, so there's not going to be any polar bonds here. But nitrogen can condense into a liquid. So that means there must be some forces in there that will hold those nitrogens together in a closer association, right? Otherwise, you wouldn't be able to make a liquid out of it. I mean, you got to get it really cold. I mean, it's got to be minus 195 degrees Celsius in order to do it. But once you get it that cold, you decrease the kinetic energy of the molecule so low that now some mysterious weak force is able to hold them together in a liquid. Okay, and those forces are due to this phenomenon, London dispersion forces. So what happens? Instantaneously, these are not permanent. Well, the dipoles that we talked about earlier, we have oxygen and hydrogen, those are permanent dipoles. They exist now and forever. But the London dispersions are temporary. They appear for a microsecond and they're gone, even shorter than that. So what happens? Well, electrons are always in motion. Right? We think of electrons sometimes as static, but they're not. They're always moving. And occasionally, they tend to accumulate on one side or the other of that molecule. Just for a brief instant, it happens. But it's long enough so that it can induce a shift in electron density in its neighbors, right? So if this one's negative, it's going to push those electrons over here. Now you've got an uneven distribution for just an instant. And now you've got an attraction. That's what's holding these molecules together at that temperature. And it has to be that temperature because anything higher than that is too much energy. It'll overcome these weak forces. So that tells you that these London dispersion forces are extremely weak. Okay. Give you a second before you get to stop spinning. These forces are always there. Every molecule has them. Except if there are other stronger forces available and the temperatures are high enough, then these are just swamped. They're insignificant. They're so small that you don't even consider them. They're only considered when these other forces are either absent or negated some way to allow the weaker forces to come to the surface and interact. Okay, so these are always there. These may not be there. It depends on the structure of the molecule. Okay, any questions about that? All right. Check the time. A little after 10. Let's see, we're good till 10:59 before we have to go in the lab. All right, let me see. Am I getting close to
Yeah, you're almost done.
getting close to shut up time? Okay. I think I've described everything on this slide already. These forces, dipoles are between polar molecules. They attract each other electrostatically so that the positives and the negatives line up. And the greater the polarity, the stronger the bond. And you can detect that strength of that bond from their physical characteristics. In other words, a high temperature melting point, high temperature boiling point means that the intermolecular forces are very strong. A low temperature boiling point, a low temperature melting point means that these forces, if they exist, are very weak by comparison. Okay. All right. Oh, here's an example. This is an odd molecule where you have fluorine and chlorine bound together. So that's not something that you find in nature. This is some chemist's idea of a fun afternoon. Create this stuff. But the difference in polarity says that fluorine is going to draw electrons more strongly than chlorine, which is true. So it will produce a polar molecule and you'll get those interactions. This is in words. So I guessed right. Fluorine, oxygen, nitrogen are predominantly the electronegative atoms that you attach hydrogen to facilitate the formation of hydrogen bonding. Let's see, factors affecting the strength of the hydrogen bonds. Okay, we talked about this one already. The electronegative element that hydrogen is bound to contributes to the movement of electrons away from the hydrogen. Also, the small size of the hydrogen nucleus, which is what? A proton. Hydrogen's just got one proton. So if you move electrons away from it, it tends to expose that positive charge. Right? If you've got a hydrogen atom here, one proton, and you've got the electron out here, then if you shift that away, it tends to expose that positive charge. And that is where the slight positive charge comes from. Okay. Our example here, this is water. So this is slight positive, and oxygen, actually oxygen has a couple of lone pair electrons, right? We did Lewis dot structures. Yeah. The lone pair electrons, they would be there even if oxygen were not very electronegative. But in fact, because it is electronegative, it tends to draw even more electron density away from hydrogens. So that's why water at 1 atmosphere and 20, 25 degrees Celsius on the surface of the Earth is a liquid, not a gas. If water were a linear molecule and it was nonpolar, then all the water on the Earth would be a gas. We'd be in big trouble. Okay, so the vapor pressures of liquids that have significant hydrogen bonding are much lower than those of similar liquids where little or no hydrogen bonding occurs. And I showed you an example of that, where we had ethanol, and then the same molecular formula rearranged the atoms into dimethyl ether, changed the polarity of the molecule, right? They're different compounds. They just have the same formulas. But that change reduced the polarity of the dimethyl ether to the point where it was extremely volatile, right? It just increased the vapor pressure massively. Okay, what's the point of this slide? Okay, we're moving from oxygen to sulfur to selenium to tellurium. Okay, so we're going down in a group from oxygen, sulfur, selenium, tellurium, and we're making the hydrides of each one. So the hydride of oxygen is water. The hydride of sulfur is H2S, H2SE, and H2TE. What we notice is that the boiling point of these increases almost linearly, increases like that. But water is funny. If it followed the same trend, water would be down here. But water's not down there. And that's due to this hydrogen bonding phenomenon. Okay. These do not make hydrogen bonds. Water does. Because sulfur, selenium, and tellurium do not have the strength, the electronegative strength required to expose that hydrogen to make it positive. So that's why it's what we say in the sciences as anomalous. Okay, these are the description of the London forces, and I've already given that to you. This is instantaneous redistribution of electron density. That's the explanation for London dispersion forces. And that explanation is required because of what we observe in nature, or what we observe from the laboratory also. I mean, you don't find liquid nitrogen on the surface of the Earth or anywhere around here. So my description using liquid nitrogen is artificial. We make the liquid nitrogen. Okay. Let's see. Here's another illustration of London dispersion forces. I used a molecule before, right, the dinitrogen molecule. But you can see London dispersion forces in individual atoms. Particularly, most instructive are the noble gases. As you go down the group, the atom gets bigger and bigger and bigger and bigger. It has more electrons out here, and they're all moving. And the more space you have, the more likely you are to get a shift, momentary shift of electrons away from one side. You can make the whole atom slightly positive on one side, slightly negative on the other. And you'll see that here. This is down the group, right? The noble gas is down the group, and you'll see the boiling point here. Helium is the coldest, and it gets warmer and warmer and warmer and warmer all the way down. And that's because with a larger atom, you have more London dispersion forces developed. Okay. With respect to intermolecular forces in a liquid, which one is the strongest? Hydrogen bonding. That is the strongest of these types of forces. And just to reiterate, which one's stronger, intra or inter? Intramolecular forces have to be stronger. Otherwise, our molecules get ripped apart by the intermolecular forces. And that's what that statement says. You have no choice. I mean, if it's not that way, then we're in big trouble. Okay. Which has the stronger intermolecular forces, right, between molecules? Well, obviously water does, because it can form hydrogen bonds. Okay, and evidence of that is in the boiling point, right? Water boils at 100 degrees Celsius, nitrogen boils at minus 195 degrees. So almost 300 degrees difference in their boiling points. Oh, I forgot this was here. So I already talked about that. Drew pictures, in fact. Okay. Now, what do we mean by ideal behavior? I mentioned this last time when we were talking about the ideal gas. These gas laws describe ideal behavior: pressure, volume, Charles' law, volume, temperature, Avogadro's law, moles, and volume. They behave ideally under conditions of high temperature, low pressure. That's because we don't want any intermolecular forces influencing the gas behavior. And that, when the temperature is high, then it swamps out any intermolecular forces that might develop. And if the pressure is low, that means there's not many of them there. So under what conditions do we have high temperature and low pressure? Right here. 1 atmospheric pressure, room temperature. Those are considered high temperature, low pressure. High pressure would be like 50, 100 atmospheres. High temperature, low temperature would be 50 K. There's one that's missing here is low moles. And that's implied by low pressure and low pressure. So fewer the moles, the more ideal. Now there are correction factors that can be introduced. Right? I haven't talked about that yet. Maybe that's not appropriate for this course. That's okay. So which one behaves more ideally? The one that has the least intermolecular forces coming to bear, the least strong, the weakest. So the weakest forces would be coming from this one because it's nonpolar. Whereas you have a difference here, and that one's going to have some stronger intermolecular forces. Okay. We talk about collisions as elastic and non-elastic. If you've had physics, then you know discussions of momentum and kinetic energy. Elastic collision, a completely elastic collision in one of which you lose no kinetic energy in the collision. It's got the same kinetic energy after as you do before. An inelastic collision is where you lose kinetic energy. And a perfectly inelastic would be like a lump of bread dough. You drop it from a height, and it gains its kinetic energy from that height right before it hits the floor. When it hits the floor, it goes. lost all its kinetic energy. So where did it go? Kinetic energy. Energy cannot be created or destroyed. Right? So where did it go? Converted it into heat. Not enough to cook the bread, of course, but there's a little bit of heat. Okay. Let's see. So we're going to put helium-filled balloons in a chest freezer. The balloons have deflated. Right? So why is that? Well, this relationship. Right? Pressure's the same. Moles are the same. Right? So what do you have? Charles' law. Decrease the temperature, decrease the volume. So we put those balloons in a freezer, cool them down, and they shrunk. So that is Charles' law, and the kinetic energy, kinetic energy increases? What gas law is demonstrated? That's Charles' law. What happens to the kinetic energy of during the warming up process? Okay. When you warm them up, the kinetic energy increases, and then the volume increases as well as the temperature. Right? Increase the temperature, increase the volume. That's fun. I used to do a demonstration. We'd have school classes from local public schools come waltz through our lab, and we'd give them demonstrations. They go to this lab and that lab, and this other lab. And one of my instruments has a acetylene flame in it. So I aspirate various liquids through it with different elements, and they produce different colors. And we'd also have some liquid nitrogen on hand. We'd take a balloon and just blow it up, and then stick it in that liquid nitrogen and just watch it go like that. Shrink down to nothing, and then pull it out, of course, with tongs, and watch it go back up like that. Okay. A gas water displacement experiment is set up. Did I describe this earlier? I don't think I did. When a reaction takes place, if there's a gas produced and you want to collect it, one way to collect it is to say, okay, if we've got the reaction in here, whatever is going on in there, the gas comes out, is evolved from that reaction. And we put the exit end of that pipe. This is water. And we have a vessel here, maybe a graduated cylinder. Right? And the gas goes up here, and this is filled at the beginning. So it has markings on it, and you can tell what the volume is, that the gas is. So as the gas collects up here, right, it just makes more space. So now we've got water there, we've got our gas up here. Okay? So we can measure the volume of that gas. The problem is, it's not just the gas in there, right? It's got some water vapor in it too. So we have to use Daltons Law of partial pressures to find out if we know the total pressure in here, which would be atmospheric, right? Roughly atmospheric, maybe a little bit less, because it's got atmospheric has to support that column of water. So you determine what that difference is, and now you have a pressure in here that's the total pressure. Then you need to know what's the vapor pressure of water. Then that added to the vapor pressure of whatever your gas is would equal to the pressure of the total. So you can measure this one, and based on the temperature, you can determine what that is. Right, there are tables that you can look up the pressure, vapor pressure of water at that temperature. Subtract it from the total, and you get the pressure of the gas. So 0.812 grams of gas displaces 350 milliliters of water. Okay, the atmospheric pressure is 750 millimeters. The temperature of the water is 20 degrees and the partial pressure of water is 18. So we've given you the partial pressure of water. So what's the pressure of the gas inside? It's 750 minus 18. Then you can use the ideal gas equation to determine the moles of your gas, because you know the pressure, you know the volume, you know R, you know the temperature, you can calculate the moles. And we also know the mass of the gas. So how do we know the mass of the gas? Can we weigh this thing? Might be easier to weigh that before and after. And the loss of mass here is the gas. Okay, so by difference, we know the gas's mass. And by our calculations, we know its number of moles. Right, there you go. Mass per unit mole. And if we do all those calculations, oh, I'm going to do them right here on the board. So there's the millimeters of mercury, and it has to be atmospheres, right, to use our R value. Okay. Then we do a calculation that gives us the moles. Right? So there's pressure, volume, gas constant, and temperature. Where's temperature? Oh, left temperature out. Temperature's got to be in here. Okay, that's an error. So we have to stick temperature in here in order to cancel out the K. Right, I need to make a note of that. Never noticed that before. Where's temperature? So we convert this temperature, add 273 to it, stick it right there. And then we know that we've got this mass and this many moles. There's our calculation, 58 grams per mole. So we could do this in the lab. A good reaction to undergo here is potassium chlorate. Just heat it up, right? Get a Bunsen burner here. And heat it up, and it'll convert to potassium chloride plus oxygen. That's not balanced, but it'll produce oxygen over here, and we can collect it and do this whole experiment ourselves. But I'm not going to make you do that. We're going to do Boyle's law today, right?
Yeah.
All right, everybody got their lab coats and safety equipment?